about bonding. So we know that all matter is made up of atoms, but those atoms don't just exist all on their own. Atoms are bonded to each other to form complex and really interesting molecules that make up all the things that we see around us. So today we're going to talk about how atoms can bond or join with one another to form molecules. So the first and probably most important thing you have to understand in order to understand bonding is something called valence electrons. These are electrons that are on the outermost edges of an atom, the outermost energy shell. And you can actually determine how many valence electrons an atom has by looking at the periodic table of elements. So remember that we call the vertical columns on the periodic table groups. And there's actually a pattern to these groups that has to do with valence electrons. So the first group over here, which contains hydrogen and the alkali metals, all have exactly one valence electron. That's one electron in their outermost energy shell. The second group, the alkaline earth metals, all have two valence electrons in their outermost energy shell. We're going to skip across this middle section of the periodic table, the transition metals, because determining the valence electrons here is a little bit trickier and not something we're prepared to do at this level. But our pattern picks up right over here in the boron group. All of the elements in this group are going to have exactly 3 valence electrons. The carbon group will all have 4, the nitrogen group 5, the oxygen group 6, the halogens will all have 7, and lastly, the noble gases will all have 8, with one really important exception, and that is helium, that only has 2. So we care a lot about these outermost electrons because in order for atoms to bond, they have to either give up, take, or share their electrons with another atom. Electrons are like atomic glue. They're what hold different atoms together. And so the number of valence electrons is going to determine whether or not an atom wants to bond and who it wants to bond with. So we need to know something else about atoms, which is that they really like to have a full energy shell on their outermost shell. And in most cases, it takes 8 electrons in order to have an energy shell. This is so important. It's called the rule of 8 or the octet rule, and we talked about it in class. Now there's one exception to this rule, which is that very first energy shell, which only needs 2 valence electrons to be full. So when you're thinking about how reactive an atom is and whether it wants to bond and who wants to bond with, you have to remember this rule of 8. So let's talk about our noble gases for a sec. They have 8 valence electrons. They are good to go. They are loving life. They already have a full, complete energy shell. So we're really not going to talk much about them in our bonding game because guess what? They don't like to bond with anybody, like to just hang out on their own. But our other electrons have our other elements have some bonding to do. So another thing that will really help us in understanding bonding is being able to draw something called a Lewis dot structure. Now, in class, we've sometimes drawn something called Bohr models, which is where we draw an atom with all of its protons and neutrons and electrons, which are great, except for the fact that some atoms have like 100 electrons, and we really don't care about all those electrons. We only care about the ones on the outside, those valence electrons that are going to determine whether or not it bonds. So a Lewis dot structure is really simple. We simply write the symbol for the element, the letter, or a couple of letters, and then we put dots to represent how many valence electrons it has. So there's a couple of examples here. This is a Lewis dot structure of chlorine, which has 7 valence electrons, and this is carbon with 1, 2, 3, and there's one hiding behind my face here, which is 4. Another really simple example, hydrogen. It has one electron, which is its valence electron, so I could put an H with a little dot next to it, and that would be my Lewis dot structure for hydrogen. So these structures are going to really help us show how these atoms bond with one another. So it turns out that there are 2 types of chemical bonds. The first is something called ionic bonds. Ionic bonds involve one atom giving its electrons and the other one taking it from that atom. And these bonds tend to form between metals and nonmetals. So if I flash back to our periodic table for a sec, remember our metals are basically all of these guys over here, right up to the staircase, right up to the diagonal line, whereas the nonmetals are these guys kind of over here hanging out on the right-hand side. So if you have a bond between somebody from the right side and somebody from the left, chances are it's an ionic bond. Now remember, as usual, there's an exception. Remember, hydrogen, although it's over here on the left hanging out with the metals, is in fact a nonmetal. So if hydrogen is bonded with one of these other nonmetals, it's not going to be ionic. It's going to be something else that we'll talk about in a sec. So here's a really simple example of an ionic bond. For instance, I could have sodium, Na, which has one valence electron. So I'm going to draw my Lewis dot structure for sodium, sodium with one dot. And I could have chlorine, which has 7 valence electrons. So let me put chlorine with 1, 2, 3, 4, 5, 6, 7. Okay? Now these guys are going to be a good fit for each other, because here's what sodium's thinking. Sodium's thinking, man, I would need 7 more electrons to have a full valence shell. You know what would be a lot easier? I could just get rid of this kind of one extra electron I have hanging out on the outside, and that way my shell that I have left will be complete. And chlorine sitting over here thinking, man, I have 7 electrons. If I could have just one more, I could have that magic 8 and be stable. So these guys are going to be great partners for one another. And what's going to happen is sodium is going to pass its electron over to chlorine. Now remember, when atoms gain or lose electrons, they become something called ions. They become charged atoms. So when sodium loses an electron, it now has more protons than electrons and becomes sodium plus 1. Chlorine, which is gaining an extra electron, now has more electrons than it has protons, and so it becomes chlorine minus 1. Now these two charged ions are going to be attracted to one another because positives and negatives attract, opposites attract. And so sodium and chlorine are going to want to hang out with one another in an ionic bond, forming a common substance that you probably consume every day in the food you eat, which is NaCl, sodium chloride or table salt. Now, the other type of bond that can form is something called a covalent bond. Covalent bonds, instead of one atom giving and another one taking the electron, both atoms put some electrons in the middle and they share them in order to make them both happy and both have that magic 8. And these bonds tend to form between two nonmetals. So again, let me flash back to my periodic table. Remember, the nonmetals are these guys over here, as well as hydrogen. So for an example of a covalent bond, I could talk about maybe oxygen and another oxygen. So 2 oxygens. Now each oxygen has 6 valence electrons. 1, 2, 3, 4, 5, and 6. And this oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. So both of these oxygens are sitting around thinking, man, if I could only have 2 more electrons, I could have a complete shell. Now, it's not a perfect world. Everybody's not going to get 2 electrons all to themselves, but what they can do is they can share 2 electrons with one another. So this oxygen can say, okay, I will put one of my electrons in the middle if you'll put one of your electrons in the middle for us to share over here. And the same thing happens down here. This oxygen says, okay, I'll put this electron in the middle if you put one in the middle that we can share with one another. And what we end up is something that looks like this. We end up with an oxygen that are sharing 4 of their electrons with one another. So in effect, each oxygen feels like it has 8 electrons, feels like its octet is completely full. Another very famous example of a covalent bond is in our very own water, H2O. Hydrogen is a nonmetal and oxygen is a nonmetal, and these guys get together and they share electrons. Covalent bonds, as it turned out, are actually stronger than ionic bonds. It pays to share. So whenever we're talking about bonding, we want to keep in mind that bonding is a chemical change. When we bond two things to one another, we are creating something new that has properties that are different than when those atoms are separate from one another. And so this is going to be a chemical change. And we can write this chemical change as a chemical equation. So for example, here I have a chemical equation. There are a bunch of atoms here that are being combined, are bonding to one another to form something new. Specifically, I have hydrogen atoms and oxygen atoms combining with one another to make water. Now, there's some protocol we have to follow when we're reading a chemical equation. So the stuff on the left, the stuff that we start with, the stuff that goes in, it's kind of like the ingredients that we're going to mix up. Those are called reactants because they're about to react or bond with one another. Whereas the stuff over here on the right, the stuff that comes out, is called the products. It's what we make. So in this case, that's water. And this little arrow in the middle kind of symbolizes that transition from one to another. We usually use the word yields or makes to describe that arrow. And I also need to know how to count how many atoms there are in my chemical equation. So whenever you see a small number like this, what we call a subscript, that's telling you how many of that type of atom is within that molecule. So for example, there are two little hydrogens here that are bonded to one another. This big number in front tells me how many of that molecule I have. So it turns out that I have two H2s. So a total of 4 hydrogen atoms. Over here I've seen O2 and there's no number in front of it, so I assume it's just one O2. So let me draw some oxygen atoms. They're a lot bigger than hydrogen atoms and my circles are having some issues here. Okay, bonded to one another. And we're going to use this stuff to make H2O. Now, when I'm writing out a chemical equation like this, I also have to keep in mind something called the law of conservation of mass, which tells us that mass and atoms cannot be created or destroyed. So however many atoms of hydrogen I have on this side have to be the same exact number of atoms of hydrogen that I have on this side. The same is true of my oxygen. If I have 2 oxygen atoms on this side, I have to have 2 on this side. And so if I look right now, this equation is not quite right as it is because I've got 4 total hydrogen atoms here, 2 times 2, and 2 oxygen. But on this side, I only have 2 hydrogen and just 1 oxygen. So I'm going to balance this chemical equation by adding one number in here, a 2. And now if I look, the number of hydrogen atoms, 2 times 2 is 4, 2 times 2 is 4, is exactly the same. And the number of oxygen atoms, O2, and 2 times a 1 is 2, is also exactly the same. So this equation is in fact balanced. I want to think about it the same way in terms of mass. So for example, if I have 1 gram of H2 and I have 2 grams of O2, I should end up with 3 grams of H2O. The total mass of all of my reactants needs to equal the total mass of all of my products. That is what the law of conservation of mass tells us. So I hope this review of bonding has helped, and good luck studying for your test.